Today we're going to talk about open sets. But first, let's review some ideas from our previous lessons. Let's let F be a complete ordered field, such as the real numbers. We'll say that a set, A, is a sequence if it's a collection of elements x sub n which are indexed by the integers n which are greater than or equal to 0. We'll say that this sequence converges to an element P if, given an epsilon positive, we can find a delta such that, in absolute value, x sub n minus p is less than epsilon whenever n is greater than delta. In this case, we'll say that x sub n tends to p, or the limit as n increases without bound of x sub n equals p. We'll say that this sequence increases without bound if, given any positive epsilon, we can find a delta such that x sub n is greater than epsilon whenever n is greater than delta. In this case, we'll say that x sub n tends to infinity. Similarly, we'll say that our sequence decreases without bound if, given any positive epsilon, we can find a delta such that x sub n is less than negative epsilon whenever n is greater than delta. In this case, we'll say that x sub n tends to negative infinity. We'll say that this sequence diverges if it either increases or decreases without bound. We'll say that our sequence does not converge if it neither converges nor diverges. Let's move on to the idea of open sets. First, we'll recall a couple of definitions. Remember that a set in the form a comma b with parentheses is the collection of real numbers x such that x is greater than a and x is less than b. A set of this form is called an open interval. Similarly, a set of the form square bracket a comma b, which is the collection of real numbers x such that x is greater than or equal to a and x is less than or equal to b, will be called a closed interval. We're inspired by the following motivating question. Why do we use the words open and closed here? Well, let's first introduce the following proposition so we can introduce some more general concepts today. Let's say that I, the parentheses from a to b, is an open interval. Then there exists elements p and epsilon such that I equals v sub epsilon of p, where v sub epsilon of p is the collection of real numbers x such that in absolute value x minus p is less than epsilon. Let's say that capital A is a sequence of x sub n's. Then the limit as n increases without bound of x sub n equals p exists if and only if, given a positive epsilon, we can find a delta such that x sub n is an element of v sub epsilon of p for all n greater than delta. Let's prove the first statement. First, we'll observe that we can write v sub epsilon of p as the collection of real numbers x such that p minus epsilon is less than x and x is less than p plus epsilon. Given two real numbers a and b, we'll choose p to be b plus a over 2 and epsilon to be b minus a over 2. We do this so that p minus epsilon is equal to a and p plus epsilon is equal to b. If this is the case, then v sub epsilon of p is indeed our open interval I. Let's show now the second statement. Let's say that a positive epsilon is given. Then we know that our sequence A converges to p if we can find a delta such that, in absolute value, x sub n minus p is less than epsilon whenever n is greater than delta. But of course, this is equivalent to saying x sub n is an element of v sub epsilon of p whenever n is greater than delta. Using this, let's make a general definition. Let's say that O is any subset of the real numbers. We'll say that O is an open set if, for each point P in O, we can find a positive epsilon such that V sub epsilon of P is completely contained inside of our set O. we'd like to use this to introduce three concepts. First, any open interval I is an example of an open set. Second, let's say that we have an arbitrary family of open sets, O sub lambda. Then the union O of the elements in this family is also an open set. Third, let's say that we have a finite collection of open sets, O sub lambda. Then the intersection O over the elements in this finite collection is also an open set. Before we go any further, let's try to write down a few examples of what's going on here. Let's say that O sub 1 is the open interval from 1 to 2, and O sub 2 is the open interval from 1 to 3. Then the union is the open interval from 0 to 3, and the intersection is the open interval from 1 to 2. So the union and the intersections are not only open sets, but they're actually open intervals. Next, let's consider the open interval from 0 to 2, and now the open interval from 2 to 4. Then the union is not an open interval, but it is an open set. This is because we have the interval from 0 to 2 union the interval from 0 to 4, but notice that the element 2 is not in this union. Similarly, the intersection is the empty set. It is not an interval, but it is an open set. This means that the empty set is an example of an open set as well. Finally, let's consider an infinite family of open sets. Here, let's consider O sub n to be the collection of real numbers x such that the absolute value of x is less than 1 over n, where n is a natural number. Then the intersection over these open sets is the singleton set that just consists of the origin. This is not an open set. We'll see why in the breakout rooms later today. This means that the intersection of an arbitrary family of open sets is not an open set. Now, let's prove the proposition. We'll begin by proving the first statement. Let's pick a point P in our open interval I. We'll denote epsilon as the minimum of P minus A and B minus P. Recall that because P is between A and B, both P minus A and B minus P are positive numbers. If X is an element of V sub epsilon of P, then the absolute value of X minus P is less than epsilon. And unpacking this, we see that negative epsilon is less than X minus P is less than epsilon. However, epsilon is less than P minus A, so A minus P is less than negative epsilon. Similarly, epsilon is less than P minus P, so epsilon on the right now is less than or equal to B minus P. This means that A minus P is less than X minus P is less than B minus P. Adding P everywhere, we see now that A is less than X is less than B, hence showing that X is an element of our open interval I. This does indeed show that V sub epsilon of P is contained in the interval I. Let's now show the second statement. Let's say that we have the union over all open sets O sub lambda in our family. Let's pick a point P in this union. Well, then this means that our point P is in one of the open sets, let's say O sub lambda 0 for some lambda 0. But we know that each of these O sub lambdas is an open set, so in particular, for O sub lambda 0, we can find a positive epsilon so that V sub epsilon of P is contained in O sub lambda 0. But anything in O sub lambda 0 must be contained in the union, capital O, so in particular, V sub epsilon of P must be contained in capital O. We show now the third statement. Let's consider the intersection O over the O sub lambdas and pick a point P in this intersection. This means that P must be contained in O sub lambda for every lambda in our family, But remember that our family only has finitely many elements. Let's denote them as lambda 1, lambda 2 through lambda sub n. Since each O sub lambda is an open set, this means that we can find positive epsilon 1, epsilon 2 through epsilon n, such that each v sub epsilon k of p is contained in O sub lambda k. Now let's denote epsilon as the minimum over these epsilon sub i's. This means that if x is in v sub epsilon of p, then in absolute value, x minus p is less than epsilon, and so x minus p is less than epsilon sub k for each k. This means that x must be an element of v sub epsilon k of p, but we already found that v sub epsilon k of p is contained in O sub lambda k, and this is true for every lambda sub k in our family. Hence, x must be in the intersection, which means x must be in capital O. In particular, v sub epsilon of p must be contained in capital O, which completes our proof. Thanks very much for watching.